20 people log on. I just want to get a sense. Most of you how many of you are graduate students? Are most of you graduate students?
Yes, 98%.
90%. And now I can actually see you. Okay. And then, so how many people are there in the room actually? It looks like 20 maybe.
Now there are 37 in the room, if they're all here,
37.
yes. And
I
then
see.
about 30 connected online.
Okay, very good. Well, first of all, I want to apologize that I cannot be with you. I would really have loved to come join you in person, but my university's rules does not allow me to travel right now. And I'm very jealous of you. You're able to see the mountains. I hope you're enjoying the shoes. I want to spend the next 90 minutes or so telling you about waves that matter. One thing I want to know, just to make sure, do you have access to the review that I wrote on the subject? I'm basically using that as my lecture notes in some sense. Do you all have that review?
Yes, we gave it, yeah, we distributed last week.
Okay, fantastic. So I might refer to that review from time to time because there's a lot that I obviously won't be able to cover, so I'll refer to it. But I strongly encourage you to read it if you haven't done so already. What I'm going to do first is to actually share screen. So most of the time I'll be using slides. And then there would be times when I want to do a little derivation, then I'll switch to a different screen to show you the derivation, okay? So I'm going to share screen now. And here are the slides. Okay, are you able to see the slides?
Yes, okay.
Fantastic. Except that I don't seem to be able to go back and forth. Hang on. Okay, so just to introduce again, my name is Lam Hui. I'm at Columbia University. I'm in New York City, although right now I'm not actually in the city. This is the review. Can you see my cursor? I can use it as a pointer.
Yes, okay.
Right. Okay, so this is the review. You can actually find it on the archive, although the version I sent to Marco is a little bit updated. It has not been updated on the archive yet, but roughly speaking, it's the same version that you can find in the archive. And the review article has a lot of references. These slides will be fairly light on references because I don't want to clutter the slides too much. If you want more background material and references, you can look at the review article. And at the bottom here, I just want to acknowledge my collaborators. Most of what I know, what I'm going to tell you, I learned from them. And I changed the title a little bit from the one that Marco gave you. Instead of fuzzy dark matter, I call it wave dark matter, and you will see why I use these terms just in a moment. Okay, so let's start with something fairly basic. We know there's rich evidence for dark matter. In fact, that evidence is why you're here. So I'm actually going to skip this, right? So astronomical measurements basically based on the gravitational effects tell us that dark matter is there. We know it exists. However, we remain extremely ignorant about very basic properties of dark matter. For example, if dark matter was some kind of particle, what is the mass of that particle? And on this slide, I just give you this huge range, right? And basically, if you look at the literature on dark matter, it can go from 10 to the minus 22 electron volts. In this talk, I would refer to that as ultralight, all the way to objects that are really massive. They are astronomical in size, 10 solar mass, for example, primordial black hole, for example. And just the fact that all these masses are in principle allowed based on what we know just illustrates the degree of our ignorance, right? However, in this vast spectrum, it turns out there's one interesting scale that you can put down just based on a very simple observation or asking a very simple question. And so let's start with that, right? So what do we actually know? Well, what we actually know is the mass density of dark matter. For example, in the solar neighborhood, we know is this number, which is probably familiar to you. It's about 0.3 GeV per centimeter cube. And that number is arrived at by measuring motions of stars, basically, in the disk of the Milky Way. Okay, so that number we know. And now we are going to ask the following question. At what particle mass would the interparticle separation be less than the de Broglie wavelength? And just to remind you here, the de Broglie wavelength is 1 over mass times velocity, of course. You might ask, what velocity should we choose? Let's choose the velocity dispersion of the Milky Way, for example, which is about 200 kilometers per second. Okay? Once you choose that number, and once you adopt this number of 0.3 GeV per centimeter cube, it's very easy to answer this question. The lower the mass, the more particles you would have in order to fulfill this 0.3 GeV per centimeter cube number, which means the interparticle separation will become smaller and smaller. And at some point, it will be so small, it's actually less than the de Broglie wavelength. The question is, what is that mass? In case you don't know or you haven't read, that mass is around here. It's about 30 electron volts. And in this talk, that's what I mean by wave dark matter. When I say wave dark matter, what I mean is any dark matter candidate whose mass is less than about 30 electron volts. Okay? And this little cartoon here is to illustrate what we have in mind. So suppose I draw a sphere, this brown sphere. Suppose it has a size which is the de Broglie wavelength. We have in mind a situation where you have multiple particles within a de Broglie volume. The smaller the mass, the more particles would have to fit inside that de Broglie volume. And therefore, almost by definition, such a dark matter particle must be bosonic. You will not be able to fit multiple particles inside the de Broglie volume if it were fermionic. So we're talking about bosonic particles. In principle, it could be spin 0, 1, or 2. In this talk, I'm going to focus on the spin 0 option, although most of the phenomenology actually applies equally well if we were spin 1 or 2. And in particular, for the spin 0 option, a light particle, a wave, basically dark matter, probably the most well-motivated candidate is the QCD axion. The QCD axion actually has a very large range in mass, but one fairly prominent mass, if you want, is 10 to the minus 6 electron volts. And that is, for example, close to the target mass of, for example, the ADMX experiment. And if you work out a de Broglie wavelength, is not astronomical, but it's actually not that small. It's a good fraction of a kilometer. So the de Broglie wavelength is actually is kind of big, at least on human terms. Now, if you go all the way to ultralight, what I call in this talk ultralight end of the spectrum, 10 to the minus 22 electron volts, then the de Broglie wavelength will be truly astronomical, right? So it's 100 parsec. And it is basically the last option that's often referred to as fuzzy dark matter. Although in this talk, mostly what I want to do is to be fairly general. Most of what I have to say actually applies equally well for any dark matter candidate that is in the wave regime. So it's less than 30 electron volts. Let me actually say just one word about what I mean by the wave regime. No? The situation you have in mind where you have many particles per de Broglie volume, you should think of that as the analog of what you have already learned in classical electromagnetism, right? If I give you a state with high occupancy, many photons, to very good approximation, such a system can be described by basically classical electromagnetic waves. or classical electromagnetic fields. So that's what I have in mind. So when I say waves, essentially what I mean are classical waves, just like the analog of classical ENF. So that is our setup.
Can I ask you a quick question, please? Why is 10 to the minus 6 EV special for the Axiom?
Why is it special? It's actually turns out to be not that special. There is actually a fairly wide range. 10 to the minus 6 electron volts turn out to be how should I say, is a mass that seems to be preferred in certain models of the QCD axions. In particular, it turns out if the relic abundance comes from a model where the Petri-Queen symmetry occurs after inflation, so that there are defects and the defects decay in the dark matter. In that kind of scenario, it seems a mass of 10 to the minus 6 electron volt is somewhat preferred.
Okay, got it. Thank you.
Yeah. In fact, maybe one of you can tell me, do you expect to have a lecture on QCD axion? I think you will, no?
Next week, yes.
Yeah, okay. So you might get a more informative answer from that lecture that you might have in the future on QCD axion. Yeah. Here I try to be fairly general, not specifically about QCD axion. Okay, good. So any other questions? By the way, it will work a lot better for me if you just speak up and ask me questions. I welcome interruptions. That would be great. Okay, so let me give you an outline then, right? So with that introduction in mind, we are going to spend maybe 5-10 minutes talking about particle physics motivations. You might want to ask, from a fundamental physics point of view, why are we interested in a dark matter candidate that is in the wave regime that's somewhat light, less than 30 electron volts, maybe even a lot lighter than that. And then I think the bulk of the lectures today and tomorrow, I want to just tell you about the wave dynamics. How does it affect how a halo works? How does it affect large-scale structure? What are the interesting phenomenologies? And then I want to end with some kind of maybe more practical points, how this wave dynamics might manifest itself in data. If you are in the ultralight regime, so around 10 to the minus 22 up to, let's say, 10 to the minus 20 electron volts, the Broglie weighting is sufficiently large that it would actually have fairly significant astrophysical implications, implications that you can verify with a telescope, let's say. So I will spend a little bit time talking about that. But even if your dark matter is not actually ultralight, let's say like 10 to the minus 6 electron volts, for example, the wave nature of the dark matter actually does have experimental implications. So I would also tell you a little bit about that. So it's kind of a unified viewpoint, if you want, on wave dark matter that span really wide range, from 10 to the minus 22 to about 30 electron volts. Incidentally, you might have the question why we even stop at 10 to the minus 22. Why not even lighter? And there is a fairly simple answer to that. Essentially, if the mass were significantly less than 10 to the minus 20 electron volts, the Broglie waving would be so large that it would be hard to conceive of dark matter that dominated galaxies that are small and they are known to exist. Basically, you will have a hard time accounting for the existence of dwarf galaxies that are dark matter dominated. So more or less, 10 to the minus 22 electron volts, more or less is the low mass cutoff. Unless you are willing to contemplate more complicated scenarios where this is only a fraction of dark matter and so on. Okay. All right, so this is the outline. Before I launch onto the particle physics motivations, let me just pause. for questions. By the way, can you all hear me reasonably well?
Yes, it's perfect.
Yeah. Okay.
I see no questions, so I think you can go. One, wait a second. I have to pass the microphone around. That's why there is a small, short delay anytime.
No problem. No problem.
So it's probably a stupid question, but what does fuzzy mean here?
What does web fuzzy mean? It's not a stupid question at all. Well, the term fuzzy diameter was introduced by these three people, Hu, Bakana, and Gruzinov. And they call it fuzzy in the sense that because of the Broadly wavelength is large, at some level, you don't really even want to think of it as a localized particle. It's kind of fuzzy in that sense. Okay. Does that make sense?
Yeah, it does. Thanks.
Yeah, that's what they meant. That's what they meant. And essentially, in this regime, it's much more helpful to think of this as a collection of waves rather than a collection of particles. And that's in fact the viewpoint I'm going to take. Yeah. And the natural question is, if you have a set of waves making, being the component of the Milky Way halo, what would it mean for what you observe or what you measure? That's kind of what we are after. We are going to be talking about that. All right. Other questions? Again, there's no stupid questions, so please do interrupt me at any point, okay? Good. Now let's talk about motivations. I'll be fairly light on the motivation because I think, at least for the QCD axion, you would have a separate lecture on that in any case. But let me start from the beginning. If I tell you I have a particle, a scalar particle, let's say even spin 0 particle, that is fairly light, a fairly natural candidate that comes to mind would be some sort of Nambu-Goldstone boson, right? If it were an exact Goldstone boson, it should be massless, as you know. The word pseudo Nambu-Goldstone boson refers to the fact that this particle is light, but is not exactly massless. And you might wonder how that happens. And probably this picture that I put here, I hope is helpful. It reminds you of a potential, right? That is a Mexican head potential. And if the head is exactly flat, it has a U1 symmetry, right? There is a whole circle of minimum that you can go around. In this Mexican head potential, you can pick any point along this circle, and it would be a perfectly good vacuum. And the excitations along the circle around that point would be a massless particle. You would call that the Goldstone boson, right? It turns out, interestingly, very often non-perturbative effects that are generally fairly suppressed. For example, some sort of instantaneous process would basically give the Mexican head potential a little bit of a tilt. Imagine in your head, you take this Mexican head potential and tilt it a little bit. In that case, this circle, not all the points on the circle are now equivalent. There will be one point that is really truly the minimum of the potential. And if it's only slightly tilted, you can calculate the curvature around that minimum, and it will be some small mass. And so this is what we have in mind when we say a pseudo Nambu-Goldstone boson. So that is going to be our canonical example. So let's imagine a particle which is really like an angle. You're just going around. There's an angle. There's a periodicity to it. It's an angular field, if you want. And it has a small mass because of non-perturbative effects. Again, the most well-known example is the QCD axion. It's perhaps the most well-motivated. It helps address the strong CP problem. Due to the lack of time, I'm not going to tell you about the strong CP problem. I think you get a lecture on that later. Suffice to say, though, in this general way of phrasing things, this axion as some kind of angular field It's more general than the QCD axion. In fact, in string theory, there are a lot of axion-like particles. It's kind of one of the predictions of string theory, essentially because string theory is the theory that demands the existence of extra dimensions. And depending on the way you compactify the dimensions, you have actually often have multiple axion-like particles. And these are particles which are the Kaluza-Klein zero modes of higher point fields. Again, due to the lack of time, I won't tell you too much about how that works. You can read these papers if you're interested.
I have a quick question.
Yes, please.
Thank you. So when that potential tilts, is there some like energy scale at which that tilt happens, or is there something that's causing that tilt, or is that just how the potential exists in nature?
That really does depend on which instanton is responsible for that tilt. For example, let's talk about the QCD axions. For the QCD axion, that tilt actually occurs during the QCD phase transition itself. It's basically the transition before which the quarks are not confined, but after which the quarks are confined. It turns out there's an instanton associated with that process that gives the potential a tilt and therefore the axion a mass. Does that answer your question?
Yes, it does. Thank you.
Yeah, so in that case, it has to do with the mechanism of confinement itself. Yeah. But there are other cases, for example, in the string theory examples, yeah, it could be other kinds of instantons. Yeah. Very good. But the key point, I guess, independent of what these instantons are, in general, these are processes that are fairly suppressed. Think of them as the analog tunneling, no? That you learn in quantum mechanics. In quantum mechanics, you probably learn, as you learn, the probability of tunneling is usually exponentially suppressed, right? It's e to the minus some moderately big number divided by h bar, for example. And therefore, it's a process we often call it a non-prohibitive process, a process that is invisible if you take strictly h bar go to zero limit. But at finite h bar, this is exponentially suppressed. And this is basically a similar kind of situation. So in general, you get a fairly small mass from this process. Okay. So that is our particle physics motivation. I do want to go through a little bit of a calculation with you. In a moment, I'm going to switch to writing on a piece of paper. I want to actually go through a little bit numerology with you on the example of fuzzy dark matter or ultralight dark matter. Why is that somehow particularly interesting from a particle physics point of view? And it's basically right here. I'm going to explain a little bit what this slide is about just to set things up. And then I'm going to switch over to paper to actually do a little calculation with you, okay? So bear with me. So when I say ultralight is around 10 to the minus 22 electron volts, although you should always keep in mind there is a spectrum. And the spectrum is actually can be fairly wide, as you will see in a moment, actually. So in this talk, whenever you see m, little m, by that I mean that is the mass of our wave dark matter particle. Let me just call it the axion, okay? Little m is the mass of the axion. We have in mind an angular field, right? I just said that before. So that is our phi here. So this phi is going to be our axion or axion-like particle. And I call it phi here. Here's a normal looking kinetic term. Yeah. Now, this field, phi, as you know, phi has the dimension of energy in 4 dimensions or mass. And therefore, when I go around this circle, associated with the size of the circle, there must be an energy scale. And I call this the periodicity scale. And the periodicity scale, I use capital F. If you read papers in the axion literature, this symbol is often used. Capital F is often called the axion decay constant. Let's not worry about why it's called the axion decay constant for the moment. For us, the important thing is F actually defines the size of this circle. It's an energy scale, okay? And as I told you already, there will be some kind of potential for this phi. If the Maxwell potential were not tilted, then there should be no potential. It should be completely flat. But because it's tilted, there will be a potential, which is basically this second term. And you might wonder why I write it this way. Well, first of all, there should be some kind of cosine because there is still an angle. And what is that angle? Well, the angle is precisely phi divided by the periodicity scale, capital F. Yeah, that is an angle. So even though I have tilted, the Maxwell potential is still true. If I go around, I would come back to myself. So this cosine basically tells you that's what's happening. You still retain some notion of this periodicity. This one is just added there so that this potential is zero. It's normalized to be zero when phi is zero. That's the only significance of that. And what is this lambda? Well, this lambda is another energy scale. Whatever this lambda is must be very small so that when you expand out the cosine and try to read off the quadratic term, the m squared phi squared term, you want that mass to be very fairly small. And in fact, if you actually do that exercise, Taylor expand, you can just read off m. It's basically lambda squared over f, okay? And for the mass to be small, therefore lambda must be very small. And precisely how small lambda is, and in fact, precisely how big capital F is, those are unknown. Those are actually depends on your Axiom model. So just to give you a sense, the Axiom decay constant, capital F, people have discussed capital F from, let's say, 10 to the 12 GeV, for example, and it can go all the way up close to Planck scale. In fact, that's the value I'm going to use at some point, 10 to the 17 GeV, somewhere between Gus scale and Planck scale. As for this lambda, that actually depends on the precise instanton process. Let's say you start with some high energy scale, which actually could be capital F itself. And your instanton process tells you that whatever potential that's created must be exponentially suppressed. So lambda would be that capital F times some really small numbers, exponentially suppressed. So this lambda is in general very small. Okay. In the case of the QCD axion, this lambda would be actually close to the QCD scale. But for us, this lambda could even be a lot smaller. And in fact, just a word of caution, this schematic form is kind of what you expect for an angular field. For the QCD axion, you would have similar kind of angular structure, although it's not precisely this potential, as probably you would learn when it comes to the QCD axion lecture. Okay, so we have this potential. This is our setup, okay? Now, the little calculation I want to show you is the following. It turns out there is a mechanism, it's called the misalignment mechanism, that allows you to compute the dark matter abundance today in a very simple way, starting from this potential. And let me tell you the idea, and then I'll switch to using paper to do a little calculation with you. Okay, so what is...
Oh, sorry to interrupt. Could I ask a question about the setup really quick before we get into the misalignment mechanism?
Sorry, say that again.
Could I ask a quick question about the setup before we get into the derivation, please?
Of course, please do. Please do ask.
Thanks. Would it be possible for the field value to get trapped at the top of the tilt or the Mexican hat potential?
At the top.
Uh-huh.
Well, at the top, it would not be a very stable thing. So,
right.
So here I sketch out the potential, right?
Mm-hmm.
Imagine this potential V of phi is basically this one.
Mm-hmm.
So this is at phi equals 0. And at some point, as you said, it would come up to the top, and then it will come back down again. So it is kind of periodic. And you could imagine a hypothetical scenario where the scalar field in the early universe is exactly at the top, perched there. is of course not a stable point. So in general, we think the scalar field is going to roll away from that top. In fact, the starting point of the little calculation I'm going to show you is going to assume some initial value for this scalar field, which is close to the top, but not quite at the top.
Okay, so there's no mechanism in which the field could get trapped, I guess, in that unstable point?
At that unstable point, yeah, it's really unstable, so any little fluctuations will cause you to roll away.
Right. Okay, thank you.
Yeah, thanks for asking.
Hi,
I love the questions. So let me just say, in a few words.
I have a question.
Yeah,
I have a question regarding the setup. So this lambda has to be small, but okay, so the mass goes with like lambda squared over f, and this whole thing must be small. But is it possible for you to have a big lambda and then the big f, like your Mexican head is super big, and then you have like a sensibly small m, but still have a big lambda?
That's certainly possible. Of course, it's in some sense, phrased this way is a very general model. You can really choose any values for these m, lambda, and f as you wish. What I have in mind is a scenario where the potential actually arises from instanton processes, where lambda is usually exponentially suppressed by some moderate size instanton action. That's kind of the idea I have in mind. But of course, in some sense, once I write this model down, you can choose anything you want, really. Yeah.
Oh, okay. Thank you.
Yeah. Thanks for asking. Despite what I said,
sorry,
though,
one more.
Yeah. Please.
Yeah, so I have a question on like the interpretation of the tilt as a mass. Could you explain that a bit more?
Okay, so it's better if I actually draw something, because it might not be so clear when I say tilt, what do I mean? So if you can focus on the piece of paper, I'm going to draw the Mascagnac potential, okay?
Okay.
So here you go. So this is my attempt to draw the Mascagnac potential. I'm going to draw a little circle down here to illustrate that it's the bottom.
I don't think we can see the piece of paper.
I think Marco is going to switch screen so that you can see.
You have to unshare.
I have to unshare. Let me unshare. Yes, I'm going to unshare. Yeah.
Now it's okay. Yeah. Thanks.
Yeah. For those of you who are online, you might want to somehow amplify that screen so that you can see what I'm writing. That screen is called Moto G for reasons that's obscure to me, because I'm using my daughter's phone to do that. Okay, so on this piece of paper, I draw a Mascagnac potential, and you see this dotted circle that's supposed to indicate basically the circle of possible minima, right? They all have equal energy, so any one point is a good vacuum, right? And by the way, this is a phenomenon, as you probably have learned, you would call a spontaneous symmetry breaking, because this potential clearly had U1 symmetry, is completely rotational symmetric. But if you pick a vacuum anywhere, let's say here, I draw a cross here, your choice of the vacuum has broken this U1 symmetry, and so we call this spontaneous symmetry breaking, right? So what was the tilt that I'm talking about? Well, imagine that this Mascagnac potential is tilted. So I'm going to just focus on that circle. Imagine that circle is actually tilted this way, so that there is a minimum that's over here. Is that clear what I mean by tilted? So if I were to draw the Mascagnac potential now, probably it would look something like this. Excuse me for the quality of my drawing. Here I'm exaggerating, but I hope this is relatively clear. I take this Mascagnac potential, I tilt it, and if I draw the circle of minimum as before, now it looks like this. And now not all points along the circle are equivalent anymore. In fact, this point clearly has the lowest energy. So this is now going to be your preferred vacuum. Does that make sense? And the terminology you would use associated with this tilting, you would say this is an explicit breaking of U1.
Like
Here, when it's flat, you can choose any vacuum you want. Your choice is a spontaneous breaking. Here, you have tilted the potential because due to instanton effects, for example. And now there is one preferred vacuum, is the state of lowest energy. I see a hand from Joseph. Is it Joseph?
Maybe then
yes.
sorry.
Yes, can you hear me?
Yes, I can hear you.
So I have just very basic question. Can it happen that this Mexican potential can be tilted so that the minimum is not in the current vacuum, and then it would roll to the minimum, or what would, can it happen?
Can it happen so that the minimum is what?
So that the tilting is done in a way that the vacuum is not in the minimum, but it's on the hill. So because now you are drawing this in a way that the vacuum is in the minimum, but can it be tilted in some different way?
Well, in some sense, the vacuum is defined to be where the minimum is. So when I use the word vacuum, what I really mean is the minimum. They are basically equivalent things. Okay. Of course, there could be scenarios where you could imagine your current, state of the universe is you are not precisely at that vacuum. You might be actually here. And in that case, you are not actually truly at a vacuum, and you will be slowly rolling to the true vacuum. That could happen. In fact, people use that as one form of dark energy, right? But that would be, in some sense, a different topic. Yeah. Does that answer your question?
It's perfect. Thank you.
Thanks for asking.
Can I ask one follow-up? This tilt, like I don't understand why you interpret the tilt as some kind of mass.
Why is it some kind of mass? Good.
Yeah.
So let's imagine I draw the potential going around the circle like this. Let me call this point the true minimum. Let me call it 0, right? So I'm now going to draw what happens if let me call the field that execute excursions around this circle. Let me call that phi. This point, let me call that phi equals 0 is at the minimum, so it's here. I'm going to draw a potential V of phi. Yeah. Now, as I climb up in this direction, the potential has to increase, so it must go like this. You agree? If I climb up in the other direction, the potential also has to increase, so it has to go like that. Yeah. And the mass is just associated with the curvature around here, around the true minimum. If you get close enough to 0, the potential must be close to m squared phi squared, right? Just doing Taylor expansion. And this m is naturally what you would call the axion mass. Of course, if you climb all the way up really high, eventually you come back down and go back to 0. So probably the potential actually looks something like this. And so it has this periodic structure. Is it clear what I'm drawing?
Yeah, thank you.
Good. I'm glad you asked. Other questions? Good. Now that we have actually this picture, let me not switch back to the slides for the moment. I'm going to keep using this picture now, right? So how do we calculate the dark matter abundance? Well, imagine in the early universe, your scalar field, the axion, has some value, which is, let's say, I'm going to put a big dot around here. This is the value. This is the initial value. Now, the initial value is, we don't know what it should be. In some sense, is really an unknown. However, given the definition of the problem, there is actually one scale. That's this little m, which is the curvature around the minimum. Remember, there is this periodicity scale. So from here to, let's say, to the top, this is around what I call capital F. If you look at my slides, actually, it should be more like, you would call that pi times F or something like that. But anyway, of the order of F. That's the periodicity scale. that actually defines the periodicity scale, if you want. And our first assumption is going to be whatever primordial value of the scalar field, let's assume is order f. Anything very different from this number, it seems to require some kind of fine-tuning. Either you fine-tune it to be exactly perched on the top, or much less than f. Seems like some kind of fine-tuning, although it's really something that's up to you. So how should I say, in the absence of further motivations, it seems kind of a natural choice. We'll just choose it to be the scale of the problem, which is the initial value for phi is around capital F. It doesn't have to be exactly F. It can be factor of 2, even factor of 10 away. It won't affect the arguments too much, actually. Okay, so we're going to choose this. Now let's ask if in the early universe you have a scalar field up there, what happened to that scalar field? If you have learned a little bit about inflation, which you might have, you know, actually in the early universe, the expansion of the universe is so fast, and it need not have anything to do with inflation. It's just in the early universe, Hubble expansion rate is just fast compared to today. If the Hubble expansion rate is fast enough, the Hubble friction would cause the scalar field just to be just stuck up here for a long time, until when the following happens. So I'm going to call the Hubble scale H, right? When the Hubble scale reaches of the order of m, which is the curvature scale, down here, then the scalar field would start rolling down the potential. Hubble friction is no longer very effective, and so it will roll down, and in fact, it will start oscillating around that minimum. And the presence of these oscillations now you can interpret as actually a set of particles. So if you want, this is the moment when the axion dark matter particles are actually born. Now you have this coherent scalar field oscillating. The oscillation amplitude reflects the dark matter abundance. And if you do the calculations right, you should be able to, using this scenario, compute what's the dark matter abundance today, which is what I now want to show you. So this is the setup. This scenario, by the way, let me give you the name. It's called misalignment mechanism. People call it misalignment mechanism because this angle, which is phi over f, if you want, so phi over f is an angle, is not actually primordially not at 0, exactly at the true minimum, but is somewhat displaced. So that's why people call it misalignment. And my assumption that the initial scalar field is of the order of f is just saying that the misalignment angle, phi over f, is order 1, basically. So that's what I'm going to assume, order 1 misalignment angle. You will see in the literature, people consider more fine-tuned misalignment angle. For example, they would fine-tune the initial phi over f to be very, very small, close to minimum. Then they would get different predictions. But here, I'm just going to show you the simplest, in a sense, the most natural kind of scenario, phi over f order 1 initially, and let's see what happens. Let's compute the dark matter abundance. That's the idea. Any questions about the setup?
Yeah, I have a question.
Yeah.
Yeah. So, the mechanism that you're describing. I mean, it looks a lot like the inflation and with the inflaton field. So, could you maybe just elaborate a bit more how exactly like this connected to the inflaton field? And also, I mean, does this process happen like after inflation ends, or is this like during
Very nice. Good, thank you. Thanks for asking. In fact, this looks a lot like the inflation, as you know. And in fact, people use this kind of idea to build inflation models. In fact, you might have read in the literature, people use some kind of axion as the inflaton itself. That certainly can be done. And initially, this initial time when the scalar field is perched up high when the scalar field is barely rolling. Clearly, this scalar field energy, this vacuum energy, if you want, or potential energy, could, in principle, drive inflation. Now, whether it drives appreciable inflation or not, that depends on the exact size of that potential. It also depends on what is your matter content in the rest of the universe. But yes, this kind of setup, it ought to remind you of inflation because it has some similarity. What we have in mind, though, is something a little bit different. This is not inflation. If you plug in the parameters that eventually we are going to use, the potential energy here is actually tiny. It's very small. And also this whole process, the way we eventually would envision it, occurs actually long after inflation ended. As you will see, actually, we work out the numbers, and I want to show you certain numbers like an ultralight M. There is some reason to think why that might be interesting, and you will see that a little bit more clearly after our derivation, probably. Yeah.
Okay, so just a follow-up. I mean, so inflation as well. After inflation, the idea is that there's in the standard, like a simple picture of the inflaton field, that there's a scalar field that decays into standard model particles, and then there's this reheating effect and everything. Yes. So we're saying that this field itself doesn't couple to the standard model particles and just, or not strongly at least, and it's just like it's a separate field with dynamics like inflation.
Good. Yeah. For our derivation of dark matter abundance, we can pretty much ignore the interaction to other fields. As an axiom, actually, you do expect certain interactions to the standard model. I think we'll come to that probably tomorrow. Let me just give you an example. The axiom has a fairly natural kind of interaction to phi coupled to the photon, basically phi coupled to FF dual, or to the gluon if the QCD axion. So you will couple to GG dual. So those are fairly natural coupling. We'll talk about that tomorrow a little bit. But they tend to be very small. And for this dark matter abundance calculation, we can basically ignore it. And yes, the dynamics is somewhat similar, reminiscent of inflation. However, we are going to apply this idea in a very different context. We are going to apply this idea where this field is perched here when the universe was actually radiation dominated. So it's long after reheating and inflation already. It's radiation dominated. The potential energy associated with it is very small compared to the energy density of radiation, and therefore the universe was not even inflating because of this vacuum energy. That's basically the setup we have in mind. Yeah. Are there other questions? Yes, one. Please.
Yeah. Okay. Can you? Okay. I have a question on these oscillations. Are these oscillations, or is that what gives you the dark matter, or does it come more fundamentally from this field?
Yeah, this would be dark matter. The oscillation is themselves. You really can interpret it as just a collection of dark matter particles.
Then, like, what is the field then? What is phi?
What is the field?
Yeah.
Sorry.
Like, what is phi? I mean, because phi has the mass of the dark matter particle. So then, what is being? I mean, how can you have particles being emitted, being caused by the phi, or this field phi?
You're asking what is phi? Well, for this, I would ask you to think about something more familiar, right? Suppose I think about classical E&M. Clearly, you are familiar with the electric and magnetic fields, right? If I give you some, field value, electromagnetic fields, you can reinterpret it as a set of photons if you want to. And in general, the classical regime is such that for some electromagnetic field configuration, usually it corresponds to a large number of photons. Basically, here we have a very similar situation. It's the same.
Okay, thanks.
I don't know whether that helps, but it's basically the same thing. It is a very similar phenomenon. Yeah. Okay. In other words,
sorry, I have another question. I'm not sure I understand why the field starts oscillating when H is comparable to M.
Okay. So for this, you actually need to know a little bit the scalar field dynamical equation. So I'm going to write down over here. So if you have a homogeneous scalar field, so I'm ignoring spatial gradient, you are going to have this equation. Have you seen this equation?
Yes, in your notes, I think.
So this is the equation for a scalar field ignoring spatial gradients. This is the derivative respect to the potential. This is phi double dot, of course, and this is the Hubble friction term. Yeah. Okay. Now let's think about what this dv phi is. Well, let's approximate. I'm going to approximate that your potential is indeed m squared phi squared. Yeah. And so when you take the derivative, you have an m squared phi here. When you take the derivative, roughly speaking. Sorry, I missed a dot here. There's a dot here. Okay, so it's phi double dot plus 3h phi dot. The potential term, the derivative is the potential, I'm going to approximate the m squared phi. Okay, and basically it's a competition between the last term. The potential wants to clearly pull the scalar field down to the minimum, right? That's what it wants to do. On the other hand, the friction term, due to the Hubble expansion, wants to slow it down. And so it's basically a competition between these two things. And the transition between which one is important is of the order of h over m. And that's actually very easy to see if you approximate phi dot. Phi dot is basically phi divided by a time scale. And what time scale could it be? Well, let's approximate that h times phi. Then the Hubble friction term is just h times h, so it's h squared phi. The potential term is m squared phi. And if you want to ask which one is dominating, you just compare h versus m. Does that make sense? Yeah, this is a fairly standard kind of argument. Yeah, you use that for inflation as well. Incidentally, for inflation, for example, you would say you want the inflaton mass m to be less than h, much less than h, so that you are friction dominated, so that the universe has time to inflate. Here we are interested in something different. When h, remember, in the universe is big, but at some point it would drop and drop until it reaches m, and then the friction now becomes comparable to the potential. The potential can start to actually pull the scalar field down. And if you wait even a little bit longer, then this term would dominate and it would start basically oscillating. Yeah. And in fact, I can say even one more thing, right? The oscillations amplitude is going to actually get redshifted by the expansion of the universe. The expansion of the universe should take energy away from the oscillation. So the oscillation would actually get closer and closer to the minimum. Yeah. And the fact that that is true, in fact, is a good thing. You can actually convince yourself the energy density associated with this oscillating field actually get redshifted like 1 over a cubed. A is the scale factor. So let me actually write here. So rho proportional to 1 over a cubed. And this happens basically to these oscillations. And that's a good thing because we want this to be dark matter, right? If it's really dark matter, it should redshift like 1 over a cubed. And this oscillating scalar field actually has that property. This is another reason why it's a reasonable thing to call this a collection of particles. Okay? Other questions?
One more, thanks. Is it possible that there could be a scenario in which reheating drives the field back up to where H and M are similar?
Yeah, that would be a very different kind of setup. So here I have in mind that this is actually in the late universe. Actually, when I say early, it's actually not that early. It's something like, as you will see in a moment, when we plug in the numbers, the redshift is like, if I'm not mistaken, maybe 10 to the 6 or something like that. It's actually not super early. It's not like inflation early. So inflation happened in the long far past. But complicated dynamics like what you suggested could happen in the very early universe, during inflation, pre-inflation. That's not the setup we have in mind, though. We have in mind something that happens long after inflation.
Got it. Thank you.
Thanks for asking. I love all the questions. I think that's great. So now let's do the calculation, shall we? I want to show you actually very simple scaling. So I'm going to switch to a different piece of paper. And now I'm going to redraw the potential, right? So this is my potential. This is phi. And I am now going to approximate this potential as roughly just m squared phi squared. Okay, I have some n squared phi squared potential. And in fact, after a few oscillations, in fact, because Hubble expansion, as I said, the oscillation amplitude get closer and closer to the minimum. And then m squared phi squared is an even better and better approximation. Okay. And now let's first ask ourselves, suppose I have this initial value, and I told you the initial value, phi initial, I'm going to call it phi initial, is of the order of f, right? I just told you that's our starting assumption. That's our misalignment angle. Phi over f is the angle order 1. Okay. Let's ask ourselves, what is the energy density? Energy density associated with this displacement of the scalar field. Well, that's easy because I told you the potential is m squared phi squared. So the energy density is just m squared f squared, roughly speaking. Yeah? You're good with that? Okay. And next, if I give you the energy density, I need to somehow find the energy density today. That's what we after. And for that, I need to know, let me call it the scale factor. I will call it A star. So I put a star here. It means this is the scale factor of the universe when the scalar fields start rolling down. Okay. I call it A star. So this is the scale factor when rolling starts. Okay, that's the scale factor. Of course, we are interested in the energy density today. And so I should take this energy density, which is m squared f squared. And as I told you, you can actually check the oscillation energy density actually redshift like 1 over a cube. So it must go like a star over a, I'm going to call it A0, which is just the scale factor today. In fact, the scale factor today is often just set to be 1. But let me just be precise. So A0 is the scale factor today. Right? So I have the energy density today is the original energy density when it starts to roll down and redshifted by 3 powers of the scale factor. Okay? All that I hope is not too controversial, not too hard to understand. Okay? So if you want, this is our step 1. Okay, let me do step 2. Well, step 2, I need to say something about actually when A star is. And here is crucial we use the fact that it starts rolling down when m is of the order of h, right? So whatever the Hubble constant is, when I evaluate at a star, is actually of the order of m. Somehow we should use that fact. Somehow that is important. Yeah? Sorry, there's no m square here. It's just m. So Hubble constant, a star is of the order of m. Okay? In fact, now I'm going to square both sides. So I'm going to reintroduce my square. I'm going to square both sides. Now we are going to estimate the Hubble constant at a star squared this way. We are going to use Friedmann equation, right? Friedmann equation tells us what? Tell us h squared is what? 8 pi g over 3 times the energy density of the universe at that time, right? And I'm going to assume at this time, the universe is sufficiently early that is radiation dominated. And so if I tell you the temperature at this time, which I call T star, I raise to the 4th power, that would roughly speaking be the energy density of the universe at that time. Are you guys okay with that? That's just T star. I'm being a little bit sloppy here. Strictly speaking, I should take this temperature to the 4th power, multiplied by the degrees of relativistic degrees of freedom. Okay, I'm going to ignore things like that in this argument. Yeah, okay. And finally, I'm going to relate this temperature to the temperature today. So this is, of course, 8 pi g over 3. T star back then is a lot hotter. The universe was a lot hotter. So if I put in the temperature today, which I call T0, this is the temperature today. I can relate those two temperatures by taking the ratio of this scale factor, right? So what is the correct ratio? I want a bigger number. So probably I want a star, or I want A0 over A star. And then I have to take to the 4th power. All right. All good. Any questions? Now we are ready to put everything together. Okay. What is the point of step number 2? The point of step number 2 is to actually tell us the relation to scaling. I just want to work out the scaling, right? M squared is scale like basically this factor to the 4th power. Yeah. So if I combine these, sorry for my handwriting, you would say m to the 1/2 is proportional to A0 over A star. Will you not? Yes. I combine this equality, I get this conclusion. Yeah. And finally, last step. I'm going to take this and plug into 1. So if I combine this into 1, I'm going to put an equality up here. So this A0 over A star goes like m to the 1/2. What I need here is A star over A0 cube. So what I have is 1 over m to the 3/2 from here. It partially cancels this m squared. So I say this goes like m to the 1/2 f squared. Of course, I'm not keeping track of proportionality factors at all, but this is the conclusion I want to draw, that the energy density today in this dark matter exhibited in the form of scalar field oscillations scale as m to the 1/2 f squared. And then the rest is just plugging in numbers. But this is basically how the argument works. Any questions about what I said? Okay, I'm going to switch over to slides now to show you what happens.
There's a question on Zoom, I think. Joseph,
yeah.
You want to speak up?
Yes,
go ahead.
Thank you. So I would like to ask about the first point, where we assume that the energy density of these field scales like a matter, like this to the -3 factor. So this is just an assumption, or this is a result of some calculation, or?
Yeah, it's not an assumption. Actually, you can show that rigorously. Do you remember the scalar field equation I wrote earlier? I wrote phi double dot plus 3h phi dot and so on, that equation. If you solve that equation, you can actually show, if you have an oscillating scalar field, how much the energy density of the scalar field would be changing with time because of Hubble friction. So when I say Hubble friction becomes subdominant and therefore the scalar field can now roll down and oscillate, that is true, but still the Hubble friction is still there. The fact that it's still there means it's taking away energy from the oscillation over time. And you can compute precisely how that energy density is redshifted by expansion. And it will go like 1/AQ. In fact, that equation kind of gave the answer away. Do you remember phi double dot plus 3h phi dot? That 3 is why you get 1/AQ actually, if you actually work it out.
Yes, I see now, thanks.
Good, yeah. Sorry, I don't have time to go through that in detail, but I trust you should be able to do that and check it yourself, yeah. It's an important check. Other questions?
One here.
Hello. So to have a pseudo ghost boson this light, 10 to the minus 22, I suppose every explicit breaking of this U1 should be very, very tiny.
Yes.
And
yes.
I see, for example, in the slide now that you put like the Axiom decay constant to be 10 to the 17 GeV. So I was wondering, I mean, it seems that these kind of particles would have a quality problem which is more severe than the one of QCD axion. So is it reasonable to assume that it will stay this light if I assume explicit breaking from, I don't know, higher dimensional operator?
Yeah, you're saying is it reasonable to assume, in other words, lambda is so small, so tiny?
Yeah, exactly. Yeah, yeah. In this sense, yes. If I want to lower f, yes, I suppose.
Yeah.
Yes.
So in this setup, in some sense, lambda is controlled by two things. One is what is the fundamental high energy physics scale. You can think of that as basically roughly capital F if you want. And then the other number that you need is the size of the instanton that generate that potential. And again, the motivation is the lambda really is exponentially suppressed, is e to the minus, basically the instanton action. And it really depends on how big that exponent is. If the instanton action is like of the order of, let's say, I believe the number is 100 or 200, it would be enough to give you such a tiny mass. So it really depends on what instanton you have in mind. And it seems, for example, in the string theory setup, it's not hard to imagine a moderate size instanton like 100, 200. It seems fairly plausible.
Okay, thank you.
But it's a good question. It's a good question. Now I want to at least wrap up this part of the discussion by just plugging in numbers. So the conclusion, based on that little calculation that I show you, is here. I'm skipping a bit of arithmetic, right? You have to plug in numbers, but the scaling is correct. You see this f squared that we did together, and the m to the 1/2. The scaling is correct. If you work out what is omega in this Axiom dark matter today, is around what you need if you assume these numbers. For example, the Axiom decay constant is around 10 to the 17 GeV. That number seems to be quite plausible in this string theory setup between Guth scale and Planck scale. And if the mass is actually ultralight, 10 to the minus 22 electron volts. So this, if you want, is one version that seems to suggest a fairly light mass is not totally crazy. In fact, it gives you the right dark matter abundance in a fairly simple scenario, I would say. However, that being said, you notice the dark matter abundance is in fact more strongly dependent on F than on M, right? It's M to the 1/2 and F squared. Therefore, if you change the axion decay constant by a bit, and you want to keep the dark matter abundance the same, then you would have to change actually the mass by quite a lot. So keep that in mind, right? So 10 to the minus 22 electron volt is kind of like a convenient number, but really there could be a fairly large range. One should always keep that in mind. Okay, and let me also point out kind of connection to QCD axion, which you might encounter. The misalignment mechanism also is one mechanism that works for the QCD axion abundance. There, the calculation is very similar, but with one difference. I want to point that out, and it's actually done in this original paper that I cited down here. The one difference is in the case of the QCD axion, the potential is only generated, as I said, during the QCD phase transition. And so the potential is in fact temperature dependent, and you have to take that into account in this calculation. Whereas in my case, I have chosen an even simpler example where the potential is just fixed once and for all by some very high energy physics. It's not even temperature dependent. And then you will get this result, okay? This is actually all I have to say by way of particle physics motivations. Let me pause here for questions.
I don't see any here, nor on Zoom.
Okay, great. Marco, can you remind me how much time do we have?
About 15 minutes left.
We have 15 minutes. Okay, good. So what I want to do now is to start telling you about kind of the wave dynamics and how it works. What are the phenomenological implications? Okay, and we are going to start with the following equation. We all love this equation. This is just the good old Klein-Gordon equation for a particle with some mass, m, right? Now, you notice, and I think it's important to point out, I have ignored self-interaction of the scalar. What do I mean by self-interaction? Let me step back for a moment. If you expand out this cosine, clearly you have a phi square term, so that's the mass term. But there would be the phi fourth term, right? Phi to the fourth term, that's the quartic term. The quartic term is, if you want, is some kind of self-interaction of the axion. It is there. In some cases, it actually could even be important. We'll talk a little bit about that tomorrow. But for the most part, for most large-scale structure or cosmology purpose, for most of them, you can basically ignore it. If you expand out to quartic term, if you call that term lambda phi fourth, let's say, you would discover that lambda, which is not this lambda, by the way, a small lambda, is of the order of m over f squared. So it's a very tiny number. And for the most part, we're going to ignore it. And in fact, there is a separate reason why it's useful to ignore it, or is justified to ignore it, is because, as I said, the oscillation actually get closer and closer to the minimum. You are oscillating m squared phi squared. Potential is in fact a very good description of the oscillation around here. You are not really sensitive to correction from m squared phi squared when you are very close to the minimum anyway, right? If you are close to back up to the top, then yes, you should think about the importance of the self-interaction. So for what I'm going to say now, I am going to turn off the self-interaction and just pretend I have a free scalar. Yeah. So this is the Klein-Gordon equation. Now, with the Klein-Gordon equation, let's think about how we might apply this equation. Typically, we are interested in using this to describe dark matter in galaxy halos, for example. And typical galaxy halos like the Milky Way, for example, the velocities of the dark matter particles is like 100 kilometers per second, much less than the speed of light. And therefore, it's very useful to directly take the non-relativistic limit. And so this is the next little computation I want to do with you. And the non-relativistic limit is also a very standard trick. Probably a lot of you have seen it already. The standard trick is the following. I take this phi, which is my axion field, is a real scalar field. I introduce a complex scalar I'm going to call psi. And for reason that would be obvious later, this is often called the wave function. Psi is just a complex scalar. Phi is the original real scalar, the axion. The trick is to factor out this e to the minus imt. And you might wonder why I do that. Well, if you factor out this e to the minus imt, this m is naturally somehow the frequency of the oscillation, no? Because you look at this equation, phi to zero order, if you ignore spatial gradient, for example, it oscillates with frequency m. Since we know that, you might have as well factor that out, and you call the leftover psi. Now, because the scalar field is not precisely homogeneous, because there are fluctuations in the universe, psi is going to have some time dependence of its own. It's not, the time dependence of the original scalar is not completely captured by e to the minus imt. So now let's write down the equation for psi. That's the idea. So from Klein-Gordon equation, it turns out after some thinking, you would deduce an equation that looks very familiar. In fact, it's the Schrödinger equation for psi. Psi is the complex scalar. And that's why, because this looks like Schrödinger equation, we usually call psi the wave function. How to go from Klein-Gordon to Schrödinger, I'm going to show you in a moment. I think in the brief time remaining, I think I can do that derivation for you. But let me also point out, going from the first to second equation, there's one interaction that is important we keep track. In cosmology, we care a lot about gravity. So even if we ignore self-interaction of the axion, we should include gravitational interaction. And so you should keep in mind that when I say box phi, this box really contains the metric in it. And we can assume the metric is, let's say, weakly perturbed away from Minkowski by some gravitational potential, Newtonian potential, essentially. And if you are careful to keep track of that, you will find the corresponding Schrödinger equation has a potential, which is this gravitational potential. Okay, so I'm going to show you how to go from Klein-Gordon to Schrödinger. But let me say one more thing before I do that derivation. In addition to this equation, you should add one more, because this equation on its own, you cannot solve it because there are two variables, right? There's the wave function, there's the gravitational potential. So how do I close this equation? I need a separate equation, which is basically the Poisson equation. I apologize, I should have written that down. The Poisson equation just tells you the Laplacian of the gravitational potential is equal to 4 pi g times the mass density. And if dark matter is the dominant mass density, then you would just put in the density of the dark matter on the right-hand side. That sources this gravitational potential. And that would close this system of equations, okay? But I will have a few more things to say about that, but let me show you that little derivation. Do I have 5 minutes, Marco, to show that derivation?
Yeah, sure. You have 7 left.
Yeah. Unless I don't have a good sense of the audience. Unless you have all seen this anyway, then I can skip the derivation.
No, I think you can show it.
I should show it? Okay, let's do it. It's actually very easy. It's also very standard. Okay, so let's do it together. So I'm going to switch out of this stop sharing, and you should focus on the piece of paper that I'm writing on. minus IMT plus complex conjugate. So once again, this is the idea, right? I factor out this e to the minus IMT. The left piece, I'm going to call it the complex scalar. But because phi is real, I need to take this and add its complex conjugate. I put a twiddle here because in front of it, there is some normalization, which I'm ignoring. Let me just ignore the normalization. Let me just look at this. Yeah? Okay, now I'm going to start taking derivatives. Okay, let's do it together. I'm going to first take phi dot. Yeah? If I take phi dot, there are two possibilities. Of course, there's psi dot, e to the minus IMT. And then, but the derivative can also hit on this. So I have minus IM psi e to the minus IMT. And then again, I should always keep in mind, I should add complex conjugate. Okay, so that is the first derivative. In the Klein-Gordon equation, we encountered second derivative in time. So I'm going to take one more derivative. So I take one more derivative. First of all, I get a psi double dot. Yeah, and then I get minus 2im psi dot e to the minus IMT. Where does this term come from? Well, the dot, for example, can hit here, and it will bring out one term. The two come from the fact that this term can also be obtained from here because the dot can hit the face and pull out the same term. So I will have this structure. And finally, the dot can also hit this term twice, right? I can hit this again and pull out another minus IM. And so I have minus m squared. I hope I'm not making any mistake. So I have these three terms. Again, as usual, plus complex conjugate, if I want to be careful. Yeah, so far so good. So now let's take this and plug into the Klein-Gordon equation now. What does the Klein-Gordon equation tell us? Well, the Klein-Gordon equation tells us that we have, I just want to make sure I didn't screw up the sign. Okay, so the Klein-Gordon equation, I have phi double dot minus Laplacian phi plus m squared phi equals 0. Here, this deserves at least one comment. When I write down this equation, I've ignored gravity. If I've included gravity, this comes from the box phi. In the box phi, I should include the metric perturbations. I'm going to ignore that now just to make the discussion simple. So I'm ignore gravity. But it's actually pretty simple to include it also. The small perturbations away from Minkowski metric. Okay, so let's now take this. I'm going to take this now and plug in basically this ansatz. Okay, from now on, I'll stop, keep writing complex plus complex conjugate. That's implicit, okay? I'll just basically focus on the e to the minus IMT terms. If I plug this in, you can see I have psi double dot minus 2im psi dots. I have minus m squared psi. You notice I have factored out the e to the minus IMT because if you look at every single term here, they are always going to have e to the minus IMT anyway. So let me forget about that. So these three terms come from phi double dot, and then I have Laplacian. So I have basically minus Laplacian of phi. Phi basically is actually just psi. I have Laplacian psi, and then I have m squared psi equals 0. So far, so good. Yeah. Now the e to the minus IMT, why was it introduced? It was introduced to basically do this cancellation. You see this minus m squared psi and plus m squared psi, they now cancel. That's actually the point of introducing this e to the minus IMT. And then I make one more claim. The claim is that psi, whatever it is, somehow is slow. Its time variation is slow. Well, what do I mean by slow? What I mean is actually precisely this. Slow in the sense that each time I take a time derivative, it's much smaller than m. So this is the idea. The t of psi is somehow much less than m times psi. That's the idea. It turns out that is the part of the non-relativistic limit. If you allow me to do that, I cross out this term also, the psi double dot. And then you see you get Schrodinger equation, huh? Just to write in the more familiar looking term, you convince yourself you get minus grad square over 2m psi. This is the Schrodinger equation. And if I had included metric fluctuation in the box, I would have gotten the potential term too. If I have included gravity, then I would have gotten this equation, minus grad square over 2m plus m capital phi. Capital phi is my gravitational potential times psi. And to supplement this equation, let me write down the other equation. So this is Poisson equation, which is Laplacian of the gradient potential is equal to 4 pi g. I need to put in a mass density, and the natural mass density is the following. Is the mass of the particle times the number density of particles. And given that I called it the wave function, you probably have a very good guess for the number density of particles. And in fact, it turns out to be correct. If you do psi square, that is the number density of particles, and you multiply it by the mass of the particle. This is, in fact, the energy density of the axion, and that sources a gravitational potential. You should put that potential into the Schrodinger equation and solve for the psi itself. And this becomes a closed set of self-consistent equations that we will spend a bit of time studying. That really tells you how to deduce consequences of this wave dark matter in large-scale structure and also in galactic halos. All right, I'm going to pause here. I think I'm running out of time in any case, but let's have maybe a few questions.
I have one quick one. I know we're kind of out of time, but so in terms of the way that we're treating gravity here, so we're treating it as a Newtonian gravity with small perturbations, but if our de Broglie wavelengths are existing on cosmological scales, doesn't GR become important?
Yeah, if the de Broglie wavelength is truly huge, then yes, you should, approaching the size of the horizon, then you should use GR. Here we have in mind that the de Broglie wavelength is not too big, right? So you might recall 1 over mv, the de Broglie wavelength is around 100 parsec. For mass, which is 10 to the minus 22 electron volt, and velocity, which is basically 100 kilometers per second. So in that case, it's still some fraction of the size of a galaxy. It's okay to use Newtonian gravity in that case.
Okay, thank you.
But it's good that you asked. There's another situation where you should not use Newtonian gravity is if you are interested in, for example, dark matter accretion onto black holes, and you want to understand the behavior of the dark matter close to the black hole horizon, you also should not use Newtonian gravity. You should go back to the original Klein-Gordon equation, which you always can anyway. Yeah.
Okay. So I don't see any other questions here. So thank you very much, Lam, again. Thank you.
Thank you.
And see you tomorrow, same time. Thank you.
Yeah, tomorrow, same time. Enjoy your day.
Recording stopped.